Okay, so far we have discussed about the basic concepts of vibration, which included few basic definitions and the causes and the effect of vibration. So far we have gone to these. In this part, we will talk about natural frequency and we will deal the stiffness of various systems, right? Now, this natural frequency, as I explained earlier, is important for the condition where free vibrations are predominant. So, we will now discuss few examples which we have already dealt with the strength basis, their kinematic basis, and other criterias. But now we will take their vibrational aspects. Right now, first example we are going to take of this cantilever beam. Right, there is a cantilever beam which is of length L and having a mass m at its free end. Right now, in strength of material, we read this that the deflection in this case when a particular load, their load is mg, is acted at the free end of a cantilever. In that case, the deflection of this cantilever beam is given by load L cube divided by 3EI, right? Where E is the Young's modulus, as we all know, and I is the area moment of inertia of that beam's cross section, right? Now, try to draw a parallel between the spring case and this deflection case. We generally know for a spring, right, if the stiffness of a spring is K unit and it is subjected to a force F which shows a deflection of X, so this relation is given by F is equal to Kx. And if we talk about stiffness, it will become the ratio of force to the displacement or deflection or change in length. Now, this conclusion can be drawn here also, by which we can get the stiffness for this particular beam. Right now, if we take the ratio of mg, which is the acting load over the cantilever beam, the ratio with delta will become 3EI divided by L cube. Right, so this is our beam's stiffness in the case when it is like a cantilever and subjected to a load at its free end. Right, this is the basic equation that we are going to compare with the different cases. Right now, if we take a different example from this thing, so this is going to be of a steel wire, or we can say for a rod as well, is been hanged from a fixed support, and here we attached a load of W. The original length of the steel wire is L unit. Right, in that case, the change in length, right, let us say because of this load there is a increase in length which is given by delta L. Right, if the diameter of this section is small d, so this change in length under the influence of load W is given by WL divided by A into E, where E is the Young's modulus of that bar. Right, now, if we say that again comparing with this F is equal to Kx kind of equation, where we got K is equal to F divided by X. Now, for this K, let us say this is K wire, the stiffness of this beam, which is given by W by deflection, which is delta L in this case, the stiffness of this sort of wire will become AE upon N, right? So this particular stiffness of this wire will decide that how much deflection or vibration will this wire show when it's subjected to a load W, right? It is sort of vibrational strength which this K represent, right? In the case of a spring, it is pretty evident, and we have studied earlier. That is why these concepts are clear, but we can draw a parallel between that spring system and this system also, right? Now, let us deal with the different cases of spring arrangement first, then we will move towards the natural frequency case, right? Spring in general are arranged in two combination. First is of series combination and second is of parallel configuration, right? If you talk of series combination, what you will get here that they are arranged in this manner, right? First spring, then second spring, then third spring, and sequential, right? There could be n number of springs in this case, right? If they are having stiffness, namely K1, K2 and K3, right? So in the series arrangement, the net deflection of the system from here to here, which is given by delta, is the summation of three individual springs deflections, right? Now, if we talk of equivalent stiffness, that means how we can replace these three springs with one spring having equivalent stiffness compared to these three springs, right? So this K equivalent is given by 1 upon K1 plus 1 upon K2 plus 1 upon K3, right? So this is the fundamental equation which characterize the arrangement is in series, right? Similarly, if we talk of parallel arrangement, right, it would be something like this: 1, 2 and 3, right? Now, if a particular load is being put over the system and these three springs are having a stiffness of K1, K2 and K3, all these three springs, in that case, when this particular portion has to remain horizontal under the influence of this load, the deflection of all three springs should be equal, right? So this is the similar equation what we have got in the series case. This is the characteristic equation. This is for parallel case and this is for series case. Now, if we talk of equivalent stiffness in terms of parallel arrangement, it will be K1 plus K2 plus K3, right? So this is the arrangement of different systems. Okay. Now, let us see how we will find out the natural frequency in any system, right? To determine the natural frequency, we have to generate a differential equation of motion on the basis of Newton's second law. Let us take a revised look over the Newton's second law. This is generally given by summation of all external forces acting upon a system is equal to mass into acceleration of that system, right? This is what the Newton's second law, and this is what we are going to use in the exercise of finding the natural frequency of various systems, right? Now let us take a very easy example. Suppose there is an inclined plane at an angle theta, right? A particular cart right here, right, having two wheels in this way, this has been attached here with a spring. This spring is having a stiffness of K, right? Under the influence of its own load, right? Suppose the mass of this cart is M, then we have this gravitational force or weight of the system, right? Here it will come out as mg sine theta, and this will become mg cos theta, right? Okay. Now, under the influence of this mg sine theta, which will try to brought down the system in downward direction, suppose this system got a deflection of, let us say, delta. Right? Now, if we talk of equilibrium, then mg sine theta must be balanced with k into delta, as we have also discussed this equation earlier. Now, if this equilibrium position is disturbed, and further we have given a displacement of x, right? Now only one force, which is restoring, will act in opposite direction, which is kx, right? Now, so by the Newton's second law equation, mass into acceleration is equal to minus of kx, right? If x is the displacement, the first derivative will give us velocity. This is the displacement. This is the velocity. And the second derivative of displacement will give us acceleration, right? In most of the books, you would find the acceleration notation in this form, so do not get confused. Now, replacing this symbol in this equation of Newton's second law applicable to this system, this will become mx double dot plus kx equal to 0, right? So this is the governing differential equation for this situation we have shown in this figure, right? Now, how we can get the natural frequency from this equation, right? We need to write this equation in this form: x double dot plus k divided by m into x is equal to 0. The standard equation of this vibrational aspect is x double dot plus omega n square into x is equal to 0. If we compare these two equations, we can get from here is omega n square is equal to k divided by m, and it implies omega n is equal to under root k upon m. So this is what the general formula of natural frequency of a system. Omega n is equal to stiffness divided by the mass of the system, right? Let us see the certain previous example we have discussed, right? In the beam's case, the cantilever beam we have discussed earlier, we got an expression for stiffness. It is subjected to a mass m at its free end. The K beam, if you remember, is given by 3EI divided by L cube. If we use this formula, omega n is equal to under root k upon m, it will give us by 3EI divided by ml cube, right? If we multiply both numerator and denominator with g and rearrange the terms, we get the expression of omega n as g divided by mg L cube divided by 3EI, right? If you remember, the deflection formula for this particular beam case is mg L cube 3EI. So this we can replace with the deflection. So the formula of natural frequency in this case will come out as omega n is equal to under root G by delta, right? Now, similarly, the example of steel wire we took earlier is like here the expression of uh, stiffness for this wire was AE upon L, right? Under the influence of mass M, similar situation we can give here is omega n is equal to under root K, which is AE divided by L upon M, which will later on become AE divided by ML, right? So there are numerous number of formulas for omega n, but the basic equation to determine is omega n is equal to under root K upon M. Having the different values of stiffness depending upon what kind of loading and what kind of ratio we get for load to deflection, the value of K will vary, but ultimate conclusion of the natural frequency is same for all the cases, right? Now we will discuss one more method to calculate this differential equation, which we got from Newton's second law, can also be calculated with the help of natural uh, energy method, right? And in energy conservation law, we read that energy of a system will remain constant, right? If we consider a journal spring mass system, right, in this way, right, suppose a mass m is here, it has given a deflection of x under its own load, right? So this is its equilibrium position, right? Now suppose this spring is having a stiffness of k, so what kind of energy that system can have, their summation always remain constant, right? Increase in one particular energy will be compensated by decrement in some other energy, but the net sum will remain constant. This is what the law of energy conservation. If we are giving it a displacement of x units, and then its velocity will be given by x dot or first derivative of displacement, right? So this system is going to have a kinetic energy. This extension would certainly cause a deflection of this spring as well, and a potential energy is also generated in this spring. So in the current scenario, there is only two energies in the system, namely kinetic energy plus the spring potential energy or spring energy, we can say. The expression of kinetic energy is half m v, which is x dot here square, plus se, which is spring energy, is half k x square is equal to constant. So this is what our energy conservation equation. Two kind of energies are involved in this system. Now if we differentiate this equation, we will get here m x dot x double dot plus k x dot, and this constant's differentiation is 0. X dot will get cancelled, then the ultimate equation will come out as mx double dot plus kx dot equal to 0. Now you can see that the previous equation which we have concluded from the Newton's second law and the differential equation we got from energy method are similar. Now if which method is convenient for what kind of problem? If we see a complicated system having too many spring arrangements, it has rotational properties also, I suggest that energy method to determine the natural frequency is more convenient compared to Newton's second law. This we will have to keep in mind, right? Another variation in this, right, in this particular system, we just concluded only kinetic energy and spring potential energy, right? If our system is having some moving part, for a case is having pulley which has considerable mass and involving inertia, we also need to include the rotational kinetic energy there, right? This and the summation will again remain constant, but the method follows the same rule. The first differentiation, and it will give us the differential equation, right? In order to calculate the natural frequency, we have to put this differential equation in its standard form, which is x double dot plus omega n square x equal to 0, right? And comparing our equation with this result will give us the final answer. Okay. Now, let us take one more example. It will give us a more clear view of making the understanding of natural frequency of system. Before that, let us see that how we can conclude the series and parallel arrangement, right, with a proper example. Now, this arrangement involves both series and parallel arrangements together. Right. Here, first spring is here, second is here, and there is a mass m right here, and it is further supported by two more springs. Right. Let us say this is K1, K2, K3 and K4. Now, first we need to apply the logic of series and parallel. In series, I have explained that the net deflection is summation of rest of the two deflections, and in parallel arrangement the deflections must be equal. This is also the method of identification whether a arrangement is in series or parallel. Right. Here we can see that from here to here, net deflection is the summation of the first spring and second spring. So we can certainly say that this particular system from here to here is in series arrangement. Again, we can see that the net deflection of this part is equal to net deflection of this part. So these two arrangements are in parallel, and these two springs are individually in parallel arrangement, right? So the upper parts net stiffness, let's say this is K dash, is equal to, and we should rather write with the formula, is 1 by K dash is equal to 1 upon K1 plus 1 upon K2. Upon solving, we can get K dash is equal to K1 K2 upon K1 plus K2. Similarly, for the lower part, the equivalent stiffness, let us say this is K double dash, is K3 plus K4. Now K dash and K double dash are two terms. As I said earlier, that these two parts, the upper part and lower parts, are in parallel because their deflections are equal. So therefore K dash or K double dash are in parallel. So the net equivalent stiffness of the system is given by K dash plus K double dash. So this is equal to K1 K2 upon K1 plus K2 plus K3 plus K4. So this is what the net stiffness of the system, right? This is what the case. And there are numerous number of springs can be placed in the system depending upon the requirement of the system. Let us take one more example of it involves two or three more kind of energies, and we will solve that problem with the energy method. Here we can see this way. uh, cylinder is out here, right? Cylinder had a radius of r. Here is the spring of stiffness k, and the mass of the cylinder is m, and the inclination is alpha. Now we need to see that how, you know, how many kind of energies are involved here. The cylinder is definitely going to get rolled down, right? So rotational kinetic energy also has involvement. Spring potential energy also there, and there is one linear energy also. Right? So we have here is kinetic energy, potential energy, spring potential energy precisely, and rotational energy. The summation of these three energies is constant. Kinetic energy is given by half m v square plus potential energy is half k x square plus rotational kinetic energy is half I omega square, right, is equal to constant. Like I said in previous problem, that v can be named as x dot, which is first derivative. So half m x dot square plus half k x square plus half I. We are familiar with the relation v is equal to r omega. So this can be written as x dot by r whole square is equal to constant, right? The value of now first differentiate this part. We can get here is m x dot x double dot plus k x dot plus I by r square, which is constant for this case, is x dot plus x dot is equal to constant. Okay. Now x dot is common in all these terms, so it will get cancelled. So the equation will come out as m plus I r square x double dot plus kx is equal to 0, right? This is also equal to 0 upon differentiation. Again, the standard form of equation, like I said, is x double dot plus k divided by m plus I divided by r square into x is equal to 0. The standard form of the equation is x double dot plus omega n square x is equal to 0. So for this case, omega n is equal to under root of k divided by m plus I divided by r square, right? K divided by m plus, we can put the value of moment of inertia for cylinder as well. It will give a more clear expression, right? So this can be done, but the procedure is like that, right? Now this is the natural frequency of the system, right? Here in this series we dealt with some linear system, with some rotational motor system, and concluded how we can find the natural frequency of the system. In the next lecture we will discuss few more systems of different cases which we will solve with energy method and or either by the Newton's second law, but we will try to expand our field in rotational problem largely in the next lecture, right? So I hope this particular concept is clear right now. So thank you, friends.